So we previously looked at what Newton derived the gravitational force to be equal to, and we're now going to see how that relates to the gravitational field strength, G. Now usually when we do our mechanics calculations, we say that G is a constant. So we say that W, or the weight, is equal to mg, or sometimes the force is equal to mg. And in this case, we assume that G is a constant of value 9.81. We can say that G is a force per unit mass. And for distances that are relatively small compared to the large radius of the Earth, we are allowed to assume that G is a constant. But we can kind of see here that G is equal to the force over the mass. So for large distances, the gravitational field strength is actually given by your gravitational force, which we previously looked at to be gmm over r squared, and you divide this by mass. And in this case, this is the mass of the small object that you're considering. So you can cancel these two little m's and you will get that your gravitational field strength is equal to g m over r squared. And remember that we said that the gravitational force has a negative sign in front of it. And this is because gravity is an attractive force. Now we've redefined what we mean by gravitational field strength. Let's do the same for gravitational potential energy. So our old equation for GPE is equal to mgh, where h is the vertical separation between 2 points. Well, we've redefined g to be minus gm over r squared. And in this case, we're now going to consider our distance h to be the distance from the center of the Earth to the point we're talking about. So in this case, we times this by r to get our equation of minus gmm over r. And this is your new gravitational potential energy equation. Now this isn't a standard proof, and you won't need to know it for your exam, but this equation is actually obtained via integrating the gravitational force equation. Now we know that gravitational potential energy is a form of energy, so we can also say that this is the work done to move an object from one point to another. And again, the reason for this negative sign here is because work needs to be done in order to move an object away from the Earth or the planet or the body we're talking about. And at r is equal to infinity, so at an infinite distance away from our planet, we are saying that the gravitational potential energy is zero. And that is because at that point there will be no gravitational force acting on an object. So we've now talked about gravitational potential energy. Let's define something called the gravitational potential, known as V. So the gravitational potential is the work done per unit mass to move an object from infinity to a point. And that is the definition of the gravitational potential at a certain point. So let's say we had some massive object here, and at this point here we have infinite distance. We have a 1 kilogram object, and we're moving it to this point here. The work done to move an object from one point to another is equal to the change in the gravitational potential multiplied the mass of the object. So if we were to rearrange this equation, we can see that V is equal to the work done over m, and I've written a subscript g here to show that this is the gravitational potential. And we know that our work done equation was minus gmm over r, and we're dividing this by m. So we get that our gravitational potential is equal to minus gm over r. And that is how you work out the gravitational potential at a point that is a distance r away from a body of mass m. Let's say now that we're going to launch this rocket from the surface of the Earth to a point that is an infinite distance away from the Earth. But we're going to assume that we're launching it to a point so that it's so far away that this rocket will no longer be under the influence of the gravitational force due to the Earth. And I want to find out at what speed do I need to launch this rocket. Well, I will need for the kinetic energy of our rocket to be greater than or equal to the gravitational potential energy this rocket has at the surface of the Earth, or at the point at where it is going to be launched from. So we know our kinetic energy equation to be a half mv squared, And this has to be greater than or equal to our gravitational potential energy equation at the point we're launching it from. So again, we know that this is gmm over r. And if you were launching it from the surface of the Earth, the value of r here would be the radius of the Earth. But just looking at a general case, well, we want to find out this velocity. So I can now cancel these two little m's and rearrange the equation such that I get that v is greater than or equal to the square root of 2gm over r. And this v here is known as your escape velocity. So your escape velocity is the minimum velocity required for an object to escape from the gravitational field of attraction. So if you wanted to calculate the escape velocity if you're launching an object from the surface of the Earth, what you could do is substitute the mass of the Earth in for m here and substitute the radius of the Earth for r here, and you could actually work out what the escape velocity for the Earth is. And what you'll notice is, for the Earth, your escape velocity is roughly 11,200 meters per second. Now, the best piece of advice I can give you after watching that video is to go off and practice some past papers or topic questions. These are single-handedly the best way to help you commit the content you've learned to memory. Obviously, go and do all the YouTube stuff of liking, subscribing, and if you found this video helpful, feel free to go and watch any of my other ones.